ENKI here. Thanks for joining us in our new series, Building MELTS 2.0, a devlog. This video is going to focus on the MELTS calibration data, taking a look at the original data, how we are sort of processing it and visualizing it in our new calibration, and then where that takes us moving forward. So let's start by switching to the screen view and we can take a look at where the project is at. So here we are in the MELTS 2.0 repository, and I'm taking a look at this original process MELTS data file. It's a Jupyter notebook that I am visualizing or viewing and working on in VS Code. You could, of course, do this in your favorite editor, including Jupyter Lab. Where we want to start with this process is the MELTS calibration data set. And actually, here, if we have database pMELTS.dat found in the data folder, this file, with its somewhat not strange, but specific format, is actually the original file that was used to calibrate pMELTS. Now, this has a lot of advantages. The fact that this is exactly the same file, which was stored in the xMELTS repository. There's actually a lot of cool things in that repo if you want to take a look. But the fact that we're using the exact same file means that any answers that we get out of building the new calibration, we can compare them directly with the existing MELTS and pMELTS calibration model. And any differences are due to differences in the methods and process that we use to build the calibration model, rather than differences in the constraining data set. Now, it should be noted that, of course, we can add new data. It has been decades since some of these models were calibrated. And so we can, of course, expand our data. And the best first stop to doing that is using LEPR, the Library of Experimental Phase Relations, something that I'm sure we will revisit later. But for right now, let's start with the original MELTS calibration data. The first half, roughly, of this file, it's actually something more like a third of the file, is the MELTS calibration data, and the bottom half or 2/3 of the file are specifically pMELTS calibration data. So, and of course, pMELTS was calibrated on the full data set. So, let's get started. The first thing we're going to need to do is take this somewhat strange format and convert it to something more immediately useful for building a model. And so what we're going to do is notice that the file has a standardized format. It starts off with an experiment number. There's a liquid number, which turns out is redundant and not very important. But there's also an author number. The author number is really a reference to a particular publication. And every publication has a unique ID. Those unique IDs are stored in this CSV file here. You can see a bunch of different reference IDs. I've called them ref IDs rather than author numbers because, I mean, that's really, really what it is, a reference to a particular paper. And then after that, we have a temperature in Kelvin, a pressure in bars, a log FO2 in standard base 10 log units, and then the 16 numbers required to specify the liquid composition. And then after that are all of the mineral phases or just in general phases. So they're usually minerals. They can also be water, fluid phases coexisting with that particular liquid. So in this case, we have an olivine with its composition expressed in weight percent of the oxides. And these are the oxides in standard order, which I'm not going to embarrass myself to try to remember. So those are the oxides in the order: silica, titanium oxide, alumina, ferric iron, chromium, ferrous iron, and so forth, all the way to water and carbon. And so, and then you have olivine, and in this case, olivine and spinel were coexisting with that experiment. As you go down there will be different things depending on conditions and on composition that are coexisting. This one only has spinel, for instance. Some of them have multiple measurements on the same phase. So you can have repeated spinels or repeated clinopyroxenes. And that's because they measured multiple times. Sometimes these can be different grains, or maybe there's zonation within a grain, hopefully not too much zonation, and they will measure different locations, and they're sort of all representative of some sort of approximation of true equilibrium. And so, we need to first start off by converting this to a standard data format that's useful. So this is the process pMELTS data notebook. The idea is to produce data files that are standard tables. I'm not going to go over the details. It's basically a lot of special purpose coding that lets you convert that into now two separate data files, a solid table and a liquid table. And we want to take a look. Those are written to the data directory. So let's take a look. That's the original file, or the processed file. But now let's focus in instead on a view of it. And you can see we have experimental indices, reference indices. So that's reference number 1 over and over and over. And then we skip to reference 49. You'll notice using the original format, each reference ID corresponds to the first experiment contained within that reference. So that's 49, and then we'll jump again to 96 and 107 and so forth. And then we have temperature, pressure, FO2, which for some reason is capitalized. I think that's just the view of it that capitalizes it. And then the liquid composition, SiO2, TiO2, in the familiar order, all the way to carbon dioxide. And then if we take a look at the solid data file, it, of course, requires experimental ID and reference ID or indices, but also an indication of what phase is present and then the composition of that phase. So now we've processed it. We have these data files. They have thousands of lines, 2,500 lines for the, 2,500 experiments in all of pMELTS, more than that in terms of lines, because you have many different mineral phases and sometimes water coexisting. But that is all we need to do with that for now. And then we need to move on to, okay, so we have this data. How do we know whether we can trust it? Like, how do we know that, like, this data is in the right format, that I haven't made a mistake in reading it in or whatever? So here we are on a validation script, a notebook that's meant to validate the MELTS calibration data, MELTS and pMELTS. So we can run this full thing. We'll start by clearing it and then running the full thing. We begin by reading in the solid table data that we just looked at, the liquid table data, as well as the reference table, which is just going to give us information about what publication each of these experiments came. You will note there is no uncertainty information attached to any of these experiments. Part of this is because many experiments do not even report it. And part of it is because these experiments were originally selected by Mark Giorso to be sort of similar in the methods that they use and the characteristic uncertainties that they use. This is something we are going to have to revisit as we build the calibration for the model. But for right now, we're going to stick with the original data file. So first, we want to ensure that the data set does contain repeated phases. So I happen to know by examination that experiment 849 has repeated spinels, and we can see that the solid data table for experiment index 849, where we know there's a repeat phase, does in fact show two spinels coexisting with similar but non-identical compositions. So that's great. That means that we didn't fail to read that in. Why do I have that check? Because the first time I did this, I did fail to read that in. I accidentally dumped every repeat. So I only had the last phase of each one. So it's really important when you build these sort of calibration work that you don't just trust that you did it right. You actually verify that you did it right. I can't believe I just accidentally quoted Ronald Reagan. But anyway, yes, we need to verify that the data and the analysis is really doing what we think it's doing. So now we want to verify some information about the reported FO2s of the experiments. So each of the experiments reports a log FO2, and they also report a ferric iron to ferrous iron ratio. At least if it contains ferric iron at all, if it has a non-zero reported value, then that should be in rough agreement with the reported FO2. The reason being, originally, when this file was created, Mark Giorso applied a liquid redox model, not the best, most up-to-date one, the Kress and Carmichael one, a previous version, but nevertheless one that should roughly agree. So we want to make sure that we're not doing something crazy. So here we're going to read in all the ones that have non-zero ferric iron, and then we're going to drop unnecessary columns, convert to moles of the oxides, and then apply the Kress and Carmichael 1991 redox model. That will give us an implied value of the log FO2 from that reported ferric iron. And then we can just calculate that difference from the reported value and the implied value and then summarize it. And we can see that the mean difference is less than half a log unit, which is really good. And the standard deviation is just over half a log unit. So indeed, they are different models that were applied. What does this mean? Moving forward, we're going to have to correct the ferric-ferrous ratio, maintain total iron, but correct the ferric-ferrous ratio to agree with our best available model, which is the Kress and Carmichael 91 model. But this is a good sign moving forward. Next, we're going to validate that the reported compositions make sense. And the best way to do that is to make sure that they add up to about 100%. Because of analytical uncertainties, they could be a little higher or a little lower, but they should be near 100%. And so for the liquid compositions, we can take just the liquid compositions, sum them up, and see that the mean is 99.5%, which is great, with a standard deviation of 1.5%. So this is really good. And even the worst case scenario is about 10% too high or too low. So possibly we might choose in our calibration, we at the very least need to renormalize these. But we may choose to exclude some of the data if they're too far away from 100%. That's something we'll have to keep in mind moving forward. And then we can perform the same thing for the solid compositions and say, we see that the solid compositions still are close to just shy of 99% for the mean, but with much higher standard deviation, plus or minus 8% on average. So this is something that we will have to keep abreast of. But we can see that it seems like the 25 and 75% marker are very close to 100%. Within 1% of 100%. So this means that this one actually probably has some strong outliers that are drawing down the mean. So that might be something that we really do want to filter for bad solid analyses. Something we'll keep in mind moving forward. But all of this looks well within the range of what we would expect for realistic laboratory experimental data. So now we want to explore finally the data characteristics. What do these data look like in terms of where they live in composition space? Where do they live in pressure temperature space? So first we'll create a few masks of subsets of the data. The most important mask we're going to focus on is the 1 bar dry subset of the data. So this is like the MELTS data, the original MELTS data without any of the water training data. Almost all the data is nominally anhydrous, except for like 6 studies at the end that do all of the calibration of the water part of the MELTS model. For this first building MELTS 2.0, we're going to get rid of water because it really simplifies things, and we're already trying to do something plenty difficult with applying Bayesian statistical analysis. So that's something we'll keep in mind. We have some functions that help us build nice plots so that we can visualize. And then we're going to plot the composition on a TAS diagram, a total alkali silica diagram. So we have silica on the x-axis and total alkalis, K2O plus Na2O, on the y-axis. Anything that's gray colored is the 1-bar dry subset of the data. And then anything that is colored is something that's hot, that either contains water, or almost all of them are really not that they contain water, but they're at 0.1 or higher kilobars. And these go all the way up to 10 GPa for a very small subset. So you can see that the gray points span pretty much the full compositional range for liquids, which is really neat. We go from basalts, or even more primitive, to rhyolites, and we have the higher alkali trends also sampled, even by the original 1-bar dry subset, the original MELTS data. And we can see, using the colors, the sort of variation of this space. We can see we have slightly elevated pressures, filling out much of the space, perhaps not quite the highest alkaline contents, but much of the space. And we can see that the highest pressure stuff, this is not surprising, are way down here in the corner, because this is the region where sort of mantle compositions will plot, really primitive compositions. So things that are up at that 10 GPa, those are really on mantle compositions, which are probably better visualized on a different diagram. But the vast majority of them fill out this space in total alkali silica, which is really nice. And then secondly, we want to look at the conditions. So we have a few more plotting functions, and now we plot the experimental conditions for the liquid table, and we're going to take an extra look at the 1-bar dry subset. And again, the gray points are 1-bar dry. This is on temperature versus log FO2, and we color code by pressure. What we can see here is that you see arrays that are sort of slanted curving. Those are roughly following redox buffers, which makes sense. These are, in general, buffered experiments. They're either on a particular buffer or slightly above or below, based on experimental conditions, below a particular buffers. So they're following that. There are a few that are horizontal. And these ones at a small negative value near 0, those are ones performed in air. So air has a slightly negative log FO2 value, so it makes sense that that's where they're living. The 0 valued ones, those are actually because they're iron free. They didn't bother to report a log FO2. And as far as the MELTS calibration is concerned, it doesn't matter. It doesn't matter that they don't report an FO2, because nothing about the MELTS model changes unless you have iron present. So that's just fine. And then we can look at the colors and see, yes, we actually fill out this temperature FO2 space pretty nicely with a range of pressures, though we do tend toward higher temperatures as pressure increases. This makes sense. This is the melting curve. As you increase pressure, the temperature has to increase if you're going to have melt present. And we also, as a result, increase our FO2s. And we can see our highest pressure points have much higher log FO2 values. And again, that makes sense with our understanding of FO2 buffers. So this is really nice. I feel like we have a good understanding of where the data are living, that we are nicely sampling a broad range of space in terms of redox, in terms of temperature, pressure, and composition. I feel like we're ready to start making forward progress on building the new MELTS 2.0 calibration. So in the next video in this series, you will see us use the existing MELTS model to calculate the predicted equilibrium conditions for each one of these experiments. And we'll be able to compare the predicted equilibrium conditions with the actual measured values. And that will be the next step on our road to building MELTS 2.0. Thanks again for joining. If you enjoy this, please do give us feedback, like, all those things. And I'll see you next time. Thanks. Bye.